Hello Legacy Sabers, Marsh here. So today you're going to graph exponential growth and decay models. What you're going to want to have on you is 4 little graph sheets of paper, calculator, pen or pencil, and then you also might want different colored pens or different colored pencils just so you can kind of show your transformations as you're graphing these graphs. But first, we have to ask a question. What would you rather have? Would you rather have option A, where you can have $10,000 given to you every day for the next 30 days, or would you want me to give you a penny today, but it will double every day for the next 30 days? Well, if I go out 10 days, I get $100,000. If I go out 9 days, I only get 512. But now, see it this way, guys. For option A, after the 30 days, I will only get $300,000. Okay? Option B. If I take option B, I will get 1,073,741,824. That is the growth and exponential growth. Exponentially growing. That is the power of exponentials. Now, when are these going to be used? When do you see these in a real life situation? You see exponential growth more than you think you do. Ultimately, things grow and decline at certain rates. Bank accounts, interest, if you ever had a savings account or ever will, you will have growth in there, and you'll need to be able to find that. Population, especially in Bismarck, we've been talking a lot about how much our population in Bismarck has been growing. Radiation decline, that's known as half-lives. Depreciation on your car, if you've ever driven it off the lot and you realize when you turn it in you get like 20% back, that's depreciation. And also carbon content of fossils. It's called carbon dating. That's how they know how old the fossil is in the ground. They can't really determine otherwise besides how much carbon is left inside of the bones. Now, what we're going to be looking at is two kinds of graphs. We're going to be looking at growth graphs and decay graphs. Now, if you notice here, guys, from left to right, you see how this graph kind of has like a up-pointing graph? This would be known as growth. It's going up. Decay from left to right should look like a slide. Now notice how my number here on my growth is a number bigger than 1. This one has a number less than 1. That's going to be our way of determining what is our growth and decay functions. So today, what is our goals? We're going to want to be able to graph them. We're going to want to be able to identify domain and range of these guys, and also we're going to look at asymptotes again. And you should be able to place them and identify them on your graph. Graphing exponential functions. Here's normally what they're going to look like. Here is the standard form of an exponential equation. Y equals A times B x minus h plus k. Now notice, guys, y equals b to the x is the parent function. That's without transformations, because all this A is a vertical stretch. This h, this is my horizontal shifting, if I'm moving left and right. And then this is my up and down shift, my vertical shift. Now, how are we going to talk about growth and how are we going to see decay? We kind of looked at that already, but here's the actual definition. You're going to be growth if your b is greater than 1. So if this number right here is greater than 1, that's how you know you are a growth. If it's between 0 and 1, aka a fraction, you are going to be in decay mode. Let's take a look at actually graphing one of these bad boys. First step on every single graph is find your parent. Find the dude without the moving. In this case, our parent would be y equals not 3, because that's technically our stretch. 2 to the x is going to be our parent. What we're then going to do is make a table for that parent. This table, unlike when we did our square root and our cube root, this table is going to change based on what our parent is. what we're going to want to do is plug in maybe like -1, 0, 1, and 2, couple of numbers. So 2 to the -1, well, that's just put 2 to the bottom, so that would be 1/2. 2 to the 0, anything to the 0 power is just 1. 2 to the first, that's 2. 2 to the second, that's 4. So this is my parent graph. I'm going to make a little sketch over here. So -1, 0.5, 0, 1, 1, 2, and 2, 4. Alright, I have made a sketch. Now, we got to take care of our vertical stretch, this 3. So that means that my y values, since it's vertical, all my y values are going to get stretched by a multiplier of 3. So my x values are not changing. I am just going to be changing my y values. So I get y equals 3 times 2 to the x. That's the problem I'm now going to be working on, my final problem. Now, we mentioned our x's are not changing, so I'm going to be -1, 0, 1, 2. But what I'm going to do to get to my new y values, I'm going to take all of my old ones and multiply it by the stretch amount. So 1/2 times 3, that's 3/2. 1 times 3, that's 3. 2 times 3, that's 6. And 4 times 3, that's 12. I now have a new function to graph. So -1, 3.5, 0, 3, 1, 6, and 2, 12, all the way up here. So now if I start to connect my dots, because I don't have any shifting going on, it's going to look something like that. Notice, guys, these guys do not cross a value. They do have a horizontal asymptote. In this case, since I did not move at all, my horizontal asymptote is located right here. And I would like for you guys to draw in your asymptotes on your graphs. So notice my asymptote's right there. I did not cross over it. If you do not shift vertically up and down, like if I would have had a plus outside, that would have been a shift vertically. If you do not do that, you will have an asymptote at y equals 0. Domain left to right, getting them all, because this is going to keep opening up, right? So this would be -infinity to infinity. Range, I am not including 0, because I can't touch it. Never get close to it, just why it's an asymptote, to infinity. Now, what is an asymptote in this regard? An asymptote, had this definition before, but it's not bad just to keep remembering. An asymptote is a line that a graph approaches more and more closely, but it never truly will touch it. So on this graph, my asymptote would be at y equals 3, right here. That would be y equals 3 on this particular graph. All you need is to basically write down this definition over here. Alright, let's try another graph here. So I got f of x equals 3 to the x minus 2 minus 5. Notice, guys, let's first identify parent graph. What is my parent? So my parent is 3 to the x. Notice this is a shift, and so is this. So I'm going to plug in -1, 0, 1, and 2. 3 to the -1, that's 1/3. 3 to the 0, well, that's just 1. 3 to the first, 3. 3 squared, 9. Pen's being a little funky today. Okay, let's go ahead and graph those. So -1, 1/3, 0, 1, 1, 3, and 2, 9. Now, let's talk about how this is shifting. I'm going to move right 2, because it's opposite of what you think it should be, and down 5 with each of those graphs. Now you could move it, you could put +2 on each one of your x values, and you can go -5 on each of those. I like to honestly just move my dots after I graphed them. So I'm going to go right 2, 1, 2, down 5. 1, 2, 3, 4, 5. Right there. right 2, 1, 2, down 5, 1, 2, 3, 4, 5, right 2, 1, 2, 3, 4, 5, right 2, 1, 2, down 5, 1, 2, 3, 4, 5. And since there is no stretch, I do not have to worry about doing one of those. So let's go ahead and connect our dots. Notice, guys, it looks like, whoop, should not be crossing 5. So I'm going to put in my dotted line here. Didn't do a very good job of not crossing it, but be careful on yours so you don't. That is my asymptote. So my asymptote is at y equals -5. Notice it matches the vertical shift. Domain, -infinity to infinity. No problems there. No holes or any of that nature. Range, I would have from -5, so I'm not crossing -5, to a positive infinity. Because remember, range is bottom to top. Now, let's try one with a bunch more added to it. So, first, let's identify our parent. Our parent is not -4, that's a stretch. It's got to be 2. 2 to the x power. So let's go ahead and draw our table here. X, y, -1, 0, 1, and 2. 2 to the -1, that's 1/2. 1, 2, and 4. Okay, I'm going to make dots here. 0, 1, 1, 2, 2, 4. Okay. Change colors. I'm going to do my stretch now. So this is going to be my stretch. So instead, I'm not going to multiply my x's though, because remember guys, it's a vertical stretch, not a horizontal. So that means vertically, I'm going to be multiplied by a multiplier of -4. So I'll go 1/2 times -4. I'll get -2 times -4. That's -4. -8 and -16. So I should start going downwards, right? Because it's a negative, so that means I have a reflection as well. So I will -1, -2, 0, -4, 1, -8, and 2, -16, all the way down there. Okay, now one more graph here to make. I have to now take care of my shifts. So that means left 1, up 3 for each of these blue dots, because the red is my first graph, this is my second, the green here is going to be my final graph. So left 1, up 3, 1, 2, 3, left 1, 1, 2, 3, and it's going to ultimately connect somewhere down there. And then I know that my graph is going to hold on to 3, because that is my vertical shift. So my asymptote is y equals 3. Domain, still -infinity to infinity, getting all the negatives this way, all the positives that way. My range, however, I am getting all of the negatives, but I stop at 3. So -infinity to 3. Last one of the night. Let us take a look. This one's a decay graph. It looks like all of the other ones we've been doing. This is growth, though it's growing negatively, kind of like national debt. This one's growing positively. And this one was a growth as well. So, first one, that is a decay graph. Still got to do my parent. Parent of y equals 1/5 x. So still got to plug in my numbers. 1/5 to the -1, that would be, -1 to both the top and the bottom. That would flip, so I'll get 5. 1/5 to the 0, that's 1. 1/5 to the first, that's 1/5. And then 1/25 for 1/5 to the second. So I'm going to put those in here. -1, 5, 0, 1, 1/5. Okay, that's that one. Now it looks like I got some shift to do. I got an up 1 to take care of, so we're going to go up 1 from each of my green dots. There we go. And then I should have an asymptote located at y equals 1, because my vertical shift shifted my asymptote. Normally would have been at 0, but since I shifted up 1, it's going to go up 1 as well. Negative infinity to infinity, and then my range, it looks like I started at 1 and I'm going up, right? So I'm getting up to 1, and then everything above it. And that's the end of this video. See you later, Sabers.